Good morning, astronomy buffs. Mr. Lally here. I am so sorry that I'm going to be out for a few days, but hopefully when I get back, I will be in a lot better shape. We are going to lose no time this week, and in fact, I'm going to get you into discussing all things related to light. There's going to be two lectures this week with some notes, and I'm going to give you some guided note sheets so that you can take notes, and I'll tell you just the most important stuff to make sure you have down in your notebook. So before we go too much further, make sure you have your guided note sheet with you, and you can take notes on that. You can pause this video anytime you want. You can also see the actual slides under slide set 8 in the class drive. Okay, so there's going to be a couple of different videos to go through over the next few days, and I hope you enjoy. So this is all about light, and light is not just the stuff that you see. In fact, we're going to be talking about electromagnetic waves and the electromagnetic spectrum. You kind of see a little GIF going on here, and you might get a sense that there's way more to this EM or electromagnetic wave business than literally meets the eye. So what we're going to do first of all is we're going to divide all waves into two different categories. We have mechanical waves. Now, those are kind of waves that are like water waves and sound. They require a medium to actually vibrate. And then there are electromagnetic waves. Those are the ones we really care about for our class. They do not require a medium, and in fact, they travel fastest when there's nothing in their way. In other words, in a vacuum. Stars emit this type of radiation or these types of waves. All electromagnetic waves travel at the same speed in a vacuum, and that speed is the speed of light. You may recall that is roughly 3 times 10 to the 8th meters per second, 3e8 meters per second, or if you're feeling a little bit specific, you can say 299,792,458 meters per second, or about 300 million meters per second, or if you prefer English units, 186,000 miles per second. Okay, so what does that look like? Well, if you were imagining light going around the Earth's equator, we've seen this before, but it would be this fast, about 7.5 orbits per second at the surface, or in this 4-second video clip, that's about 30 orbits around the Earth. That's pretty fast, 7.5 orbits around the Earth's circumference in 1 second. You can also imagine light going up to the moon, out to the moon, not up, out. And that takes about 1 second, 1.3 seconds or so to go out, 1.3 seconds or so to come back. And I think I've shown this to you for Mars as well. Mars is roughly 3 light minutes away under the best of circumstances. And I won't show you the whole video here, but you can see just how slowly it seems to be going. Even at the speed of light. The speed of light is a remarkably fast speed, but really in cosmological and astronomical terms, it's kind of slow. So it's no real wonder that we don't get too far in the universe. We can't go that fast. All right, taking a look at the EM spectrum. Well, all electromagnetic waves can be represented on a chart. Generally, we break it down into 7 major categories, and we almost always go from low frequency, which are called radio waves, to high frequency, known as gamma rays. Now, you can also think of this as long wavelength to short wavelength, and let's take a look. Okay, so the general electromagnetic spectrum is broken down into radio, microwaves, infrared or IR, visible or Roy G. Biv, which of course stands for red, orange, yellow, green, blue, violet, UV or ultraviolet, X-rays, and finally gamma rays, the highest end of the spectrum. This is a little brief video interlude here. I'm not going to actually show this right now. You can take a look at this. It's linked in the notes. Nothing's super earth-shattering about it, but it gives you just a slightly different perspective. Now, this formula is actually incredibly important. I don't think you've seen a formula quite like this before unless you've had physics. This is called the wave equation, the wave speed equation. And it simply says that c, which is the speed of light, you may remember that stands for constant, and celerity or celeritas. Speed of light is equal to frequency times wavelength. That Greek letter on the right there is known as lambda, and that is the wavelength of light. So c is the speed of light at meters per second, 3 times 10 to the 8th meters per second. F is the frequency of light in hertz, which means waves per second or cycles per second. And lambda is the wavelength of light in meters. The one thing that's probably not super obvious about this, but you do need to understand, is that as the frequency goes up, The wavelength goes down, but the speed stays the same. We're going to see this in an analogy here in a minute, but again, in terms of electromagnetic spectrum, radio waves have a really big wavelength, but they have a low frequency. At the other end of the spectrum, gamma rays have a short wavelength, but a high frequency. No matter what, the product of frequency and wavelength remains the same for EM waves in a vacuum. Here's the analogy I was talking about. Imagine we have two kangaroos. At first glance, it looks like one's going a whole lot faster than the other, but you see that they cover the same distance in the same amount of time. Kangaroo on the top has more hops per second, but the distance between the hops is shorter. Kangaroo on the bottom, fewer hops per second, but the distance between the hops is greater. So this is analogous to low frequency, long wavelength waves on the bottom, higher frequency, shorter wavelength waves on the top. Another picture of the EM spectrum for you. At some point in your notes, you definitely want to have some kind of EM spectrum shown. You might find this particular one is the easiest one to wrap your head around, but definitely have some picture of the EM spectrum in your notes. So yep, the electromagnetic spectrum includes all forms of light energy from radio to microwave, infrared, visible, UV, X-rays, and gamma rays. You might notice at the far end there they show a little comic of the Hulk. And that's because in classic Marvel fashion, Bruce Banner became the Hulk by being exposed to gamma rays. Gotta tell you, in reality, if Bruce Banner were exposed to that much gamma radiation, he'd just be the dead Bruce Banner, not the Hulk. All right, I got some examples here that you want to be familiar with. Radio waves include all types of communication. That includes things like standard radio waves that you might be listening to, television, satellite radio, Wi-Fi, Bluetooth. The information we get from radio waves tells us a whole lot about stars, their age, their temperature. Cell phones communicate in the radio range of the spectrum. Then you get microwaves, also used for communication, though not so much for us. Wi-Fi. Of course, in cooking, then there's a whole lot of background microwave radiation in the universe. Infrared or IR is also known as heat. You actually get IR emitted from some remote controls to control televisions. Visible light, or Roy G. Biv, that's the EM waves that our eyes are sensitive to. UV, ultraviolet, that can be used for killing bacteria and cleaning. Actually, it gives suntans, it gives skin cancer too with overexposure. X-rays, of course, are used in medical purposes. The nice thing about X-rays is that the low-frequency X-rays will pass through skin, but not through bone. Of course, they have to be low enough frequency to not do any major damage. And then, of course, gamma rays are also used in medical, but they are quite dangerous when in anything other than the smallest amount of doses. Still, they can be used to help fight tumors in the right types of applications. Again, going in this particular list, I'm going from low frequency, long wavelength at the top of my list to high frequency, short wavelength at the bottom of my list. Well, the sun, of course, our nearest star, emits I guess you could call this a fingerprint of the sun's radiation. It's sort of a general picture of the light / EM waves that the sun emits. It's a little backwards, however. It's going in order of increasing wavelength. That's why you have UV, then visible, then infrared. You actually are missing parts of, or I should say this picture is missing parts of the solar radiation spectrum. There's actually some stuff up here that is beyond UV, which would be X-rays and gamma rays. There's some stuff that's beyond the infrared range. There's a whole lot of radio range light or EM waves that are given off by the sun. The sun is a pretty great example, however, of a typical star that emits a whole lot of different types of EM waves. So what does it look like? Well, when we see the sun, we kind of see one color, we basically see something in sort of the yellowish orange range. We don't see all this other stuff. We don't see anything outside of the visible range. We don't see anything beyond UV. We don't see anything below visible. All we see is the color. that we are kind of peak sensitive to. However, there's a whole mess of stuff. And if you could actually see the sun in different radiation ranges, it would look very different. Oh, actually, that's a pretty cool picture. You've got the sun setting that's taken from Earth on the left and then from Mars on the right. I love that picture. Okay, that's actually one of my pictures of the sun. That's taken in a pretty specific visible wavelength. You see just how plasma-like the surface is. Those dots there are, of course, sunspots. We'll be taking a look at those more carefully in a couple of weeks. There's the sun in radio. These are false color images, by the way. You can also kind of get a sense of just how kinetic it happens to be. Sun in radio range. That's the sun in infrared. And then visible, 653 nanometers red. Visible light. There's the UV, low UV range right there. Shorter UV range. Shorter still UV range. And then the shortest UV range in this particular sequence. Then you got the sun in X-rays. The sun looks very, very different if you happen to have infrared eyes versus just having visible light eyes, which is what you kind of see there through a filter. Yeah, the sun looks really different at different ranges. Hey, this is my favorite X-ray. I don't know if you can see the resemblance between that and me, but that's me. The staples aren't there anymore, but the titanium bolts still are. If you like, there is a much greater detail EM spectrum that's linked there. It's kind of, I'm warning you, it's kind of a crazy, very, very detailed spectrum picture. We are constantly, continually bombarded by EM waves, most of them pretty safe. We are really protected by the most dangerous stuff from the sun, by our ozone layer, by our atmosphere. We don't get hit by the X-rays and the gamma rays and the UV rays, the dangerous, super dangerous UV stuff from the sun. We do get hit by a lot of UV, low UV range stuff, and that can still cause sunburns and skin cancer with repeated exposure. So as you know, when you're going to spend a lot of time out in the sun, you really do want to use a form of a sunblock. It is absolutely demonstrated to help protect your skin. Last thing I want to mention here is kind of a bit weird, maybe a little bit esoteric, but what are electromagnetic waves really? What are they actually? And I have to say there's just not a simple answer to that question. What you're kind of seeing demonstrated there are these oscillating sine waves, and they're actually perpendicular to each other. Now, sine waves may not mean anything to you right now, but an electromagnetic wave does actually have two parts. It's got the electric part, and it's got the magnetic part, and these two things are perpendicular. That means they're at right angles to each other, these two fields. And it actually gets stranger because there are situations in which electromagnetic waves don't act like waves, but rather they act like particles. Like if they collide with particles, for example, they actually scatter like billiard balls. And I guess all this kind of leads us to say that light is not a wave exactly, and it's not a pure particle. It's kind of something different. So we generally refer to light in terms of things called photons, and we do that to distinguish it in certain situations. But for us right now, it's going to be okay to refer to light as a wave because in the context that we care at the moment, it is wave-like. So that concludes this first part of the light video. When we come back, we're going to be taking a look at other characteristics, ways we use to measure light, and get all sorts of information from light. We're going to be looking at starlight, how we classify the colors, how we classify these things called the magnitude, which measures the brightness, and then how we put it all together with motion, and that's where the Doppler effect comes in, and how stars compare to each other, which is where the HR diagram comes in. Okay, see you shortly.